I wanted to leverage AI. I wanted the AI to help us provide a reasonable explanation as to what's going on with the metrics.
Hello, everybody, and welcome to this edition of the Ampere Developer Impact. I'm joined today by Karan Kamatgi from the Application Performance Engineering team here at Ampere. And we're going to talk about the Ampere PMU Profiler. Karan, we've already had a deep dive interview just a few weeks ago on the Ampere System Profiler. Can you explain to me how the Ampere System Profiler is different from the Ampere PMU Profiler, or ASP and APP as we call them affectionately, and when you would reach for Ampere PMU Profiler in addition to what you can get from the Ampere System Profiler?
Thanks for having me, Dave. Yeah. So, as a performance engineer, I would categorize root cause analysis into three different buckets. And the first bucket is going to be your system health, where you broadly look at all the sub components that you have on your platform, and ASP really fits that bill perfectly. It kind of gives you the overall system health that you want to look at. And the second bucket is your application health. So essentially looking at your hotspots in your code. There are multiple tools that help you get there, like for example gprofng. And the third bucket is really the microarchitecture analysis. That's where APP fits in perfectly. It kind of gives you the workload signatures that you want to know and understand, and it does that so by using PMU counters, which there are two of. So one is the fixed counters. For example, CPU cycles is one such example, and there's also the other class which is the programmable counters. So APP kind of lets you collect these PMU counters, which you can collect, analyze, and understand where your bottlenecks could be.
Okay. And can you explain for those unfamiliar what PMU means, what a PMU counter is, and for example, how the modern CPU pipeline looks like, and how PMU counters fit into that?
Sure. So a PMU is a performance monitoring unit. It's part of your the core. So it's a piece of your hardware that allows to understand how CPU is behaving while your software runs. Right. Think of it like your fitness tracker for your processor. Right. How many instructions are being executed, how often it has to wait for memory, and things like that. Right. So we want to know where those stalls are, where those bottlenecks could be, and PMU is one way of getting to know these things. And like I said, so there are two different PMU types. So one is the fixed one, which is CPU cycles, and then we have the programmable one, which you can essentially program these counters with hex code that allows you to collect specific events, right? And when you collect these events, you can group them, and APP does this for you, so you don't have to do any of these things. Modern CPUs these days, they have multiple strategies to use all the resources efficiently that are available. And one such strategy is pipelining. Right? So when you talk about pipelining, there are multiple stages in which the execution happens. The first stage is your front end, wherein instructions are kind of fetched using iCache. They are then decoded, and when the decoded instructions land in what we call the micro-op queue. Right. So once these decoded instructions land in the queue, we call them micro ops, and these micro ops are then picked up by the scheduler. And when the dependencies are available for it to be executed, it is then fed into what we call backend. And this is where most of the execution happens. Your ALU, arithmetic logic unit, and a few others that are your execution engines. Those are all happening in the backend. And if there is some data that is not available for the operand to be executed, then it waits for that data from Dcache. And once the data is available, it then executes it. And once the micro op is completed, it's then retired. Right. So that's essentially your work is complete when it reaches the retiring stage.
In summary, all of these are happening at the same time, right? You will have instructions being cached, instructions being fetched from iCache while data is being fetched from
Absolutely.
Dcache and instructions are being retired. So that's what the pipeline means, is everything is running kind of at the same time, right?
Absolutely, and also the the back end. So whenever the instructions are available for execution, it just executes, which means it is out of order execution. So
Okay.
essentially, it will not wait for it to be available. It just executes as soon as it's available. So that's one way to keep all the resources useful.
And so the Ampere PMU Profiler has probes on every single event in the CPU pipeline, whether that's fetching instructions, decoding those instructions, using parts of the CPU core other than the instruction processing unit itself, and then kind of follows the instructions all the way to the end. Is that basically correct?
Yep, yep, yeah. On a very high level, yes, that's
Okay.
absolutely correct.
And what does the output of the tool look like? Like how are those events characterized and presented to a user in a way that makes them, a little bit more understandable for people who aren't familiar with CPUs?
Sure. So, the tool right now gives out two outputs. The one is CSV that kind of gives all the metrics, and these are all numerical numbers. And also, it gives out a sunburst chart. Right. So, think of it like a level categorization. So, you have level one, level two, level three, and level four. TDA, what we call top-down accounting categorization. And essentially, when you look at this particular sunburst, you look at the center of the sunburst chart, which is the pipeline, which is what we explained previously, and that's your 100% of your pipeline cycles. And we want to look at where those cycles are being spent. So you level one kind of gives you that categorization, right? So right now you can see it's 65% backend bound, which means it's waiting either for memory or core, whatever the resources are in the backend. So it's kind of stalling a whole lot. And there is the other category, which is retiring. Like I mentioned previously, it's the useful work. So essentially, you would want more of your cycles to be retired, and that's the useful work done. And front end bound means it's trying to fetch those instructions, but for whatever reason it's stalled fetching those instructions and decoding them. And there is this fourth category, which is lost. So essentially, there are different strategies where we prefetch instructions, and those prefetch instructions might not be useful during execution. Right, that's kind of wasted. So we categorize it as lost. And essentially, we would also have to flush those instructions because we have to get new instructions in the pipeline.
So in general, here you're going to want more green, less blue, less red in your CPU chart. Can you walk us through how somebody can make sense of this graph and its information and actually generate some actionable insights from it? Do you have a real life example that you can work us through?
Recently, when we looked at one of the workloads called DGEMM, and we were looking to scale this particular workload, in the sense, we know that it scales with increasing the matrix size. And so we wanted to look at the throughput and wanted to see where the peaks are. And to our surprise, it kind of plateaus at around 1 point, so 12,600, around that particular range. It kind of plateaus at around 3.6 teraflops. And we were trying to figure out why the performance is kind of plateauing there, and why is it not scaling with matrix size. In theory, matrix multiplication is kind of memory bound. So that was one of our theories. Maybe there is a bottleneck around DRAM bandwidth. Maybe it's running out of bandwidth and it's not scaling. So that's one of the theories that we had. So when we ran APP, and to our surprise, we saw, the workload is mostly backend bound at level one, which means it's kind of stalling, trying to wait either for. So when we look at level two, there is no memory wait at all. So it's around 7%, which is, but the major bottleneck was at the core. So it's waiting on the core. So there is definitely core pressure. When we look at level three, there is resource pressure, and I was kind of curious what kind of resources is it waiting on. And in level four, it kind of reveals that it's waiting on the floating point execution engines, right? There and with this particular workload, we were kind of hitting the theoretical limits. We could only do two floating point instructions per cycle, and we are kind of hitting that limit. So unless we had, run APP and got to this level of analysis, we would have never understood where the real bottlenecks of this workload were.
What were you able to do with this information? Like, how did you go about optimizing this to avoid needing the floating point unit, or to reduce the amount of time that you were spending in waiting for the resource?
Knowing the limitations, it allows us to review our data structures. So, having a working set that can absolutely do lesser of floating points, so that we don't hit the theoretical limits. And that kind of help boosted IPCs as well, which is instructions per cycle. And also, the scores were kind of linearly scaling once we were
Right.
able to review our data structures, right? And kind of also give feedback to our CPU architects, right? Because it kind of helps building our next gen CPUs.
So it's providing both input back into the CPU designer, and but also the actionable insight for the people who were doing this matrix multiplication was, you need to change your data structure, you need to use less floating point, you need to maybe change the way that you're calling into this to use smaller tile sizes. It required changes to data structure and algorithm.
Absolutely.
Another example that you talked about when we were preparing this was using APP to detect false sharing. Do you want to maybe talk about what false sharing is and how you can detect it with APP, and the ways in which that's also potentially algorithm and data structure bound?
Yeah, so fault sharing is an interesting phenomenon in that when two or more CPU cores update, different variables, they're not, connected to each other, but they're different variables that happen to somehow sit on the same cache line, right? So when even though the threads that are not logically sharing the same data, the hardware kind of tracks the ownership at the cache line level, right? For example, 64 bytes, right? And not per variable. So when one core writes its variable, the other core's copy of that whole line has to be invalidated, right? So if another core then writes to its own variable on the same cache line, the line bounces again, right? So this repeated back and forth is often what we call coherence ping pong or fault sharing, right? So there is an immense performance impact to this, right? So fault sharing can cause large slowdown in, especially in multi-threaded environments where the CPU spends a whole lot of time on coherence traffic instead of doing the useful work, right? And it also has to do lots of invalidations, ownership transfers between the cores, right? So it kind of, does a lot of overhead work instead of doing the useful work.
And what do the PMU probes look like when you see false sharing compared to when you don't see false sharing?
Definitely, for detecting fault sharing, we do have a few metrics that APP allows us to collect. And, cohesively, we would like to look at the whole context, right? The context would involve with fault sharing, your IPC kind of drops. Your IPC is instructions per cycle, so that the amount of useful work that you are doing. So as you can see, with no fault sharing, you were doing 1.17, which is good. Anything in the range of 1 to 2 is good. 2 greater than 2 is even better. But if you look at the suspected fault sharing, it's dropped to 2.47. So essentially, your useful work has reduced. And we would also want to look at coherence related PMUs, right? For example, you have L2 cache invalidations, which is kind of, looking at how many L2 cache invalidations are happening per thousand instructions, right? And if you see, it's shot up immensely. It's gone to 6.74. We would also want to look at L2 snoops. So by snoops, I mean mostly snoops are what we call a coherence check. So when one core wants to read or write a particular cache line, the system would like to know, is there any other copy that is owned by another core, and maybe it wants to invalidate that particular copy, right? So the system has to constantly check on this particular cache line, and this constant checking is what we call snoop, right? And during fault sharing, invariably there is a lot of snoop activity going on. And as you can see, it has shot up from zero point zero 0.06 to 6.85, which is huge. We have recently added this new metric, which we call L2 cache invalidation per Snoop. So essentially, every Snoop is ending up in a cache invalidation, which means, essentially, there is a lot of Snoop activity going on, and this Snoop activity is resulting in cache invalidations. So the core has to essentially do a lot of this coherence work instead of actual useful work. As you can see in the suspected fault sharing, it has shot up all close to one. So essentially, which means, every Snoop is ending up in cache invalidations, which is not good. Cohesively, we also want to look at SLC misses. That's something we want to look at when we look at the overall picture. IPC dropping, you have these coherence related PMUs that we want to look at. We also want to look at how much of your last level cache misses happening, and if it has shot up, then definitely it's a signal that there is fault sharing going on within your system.
So to summarize the mechanism, right? Anytime that you have a cache line that's shared across multiple cores, when one of those cores writes to the cache line, it triggers a snoop for every single copy of the cache line. And if one core has written to the cache line, all of those other copies of the cache line are invalidated. Let's say you've got 8 copies of a cache line, that writing in one generates 7 or 8 snoops, and each of those snoops then invalidates a cache line, and the cache line requires updating. I can see how that generates an awful lot of overhead for somebody who's not so familiar with that stuff, who has a really high level understanding of how the computer works. How do they take this analysis and generate meaningful, actionable, and simple, like something that they can act on at their level, advice on how to avoid the problem?
Yeah, funny you asked that. So recently, I worked on a POC, wherein I wanted to leverage AI, especially in this AI world. I wanted to see if AI can help us with, PMU analysis, and that's one of the POCs that I recently worked on. Wherein, I wanted the AI to help us provide a reasonable explanation as to what's going on with the metrics, because we already have the top-down analysis metrics that we have previously looked at. Now we want to look at the explanation of these metrics, what these metrics really mean. Like an end user like yourself, maybe you're not fully aware of what these metrics really mean, how they translate into the actionable items, right? So that's where I wanted to leverage AI. Here's the primary output of the LLM, right? It's kind of summarizing. Initially, we need to provide it context as to what the workload is that we are trying to profile, and on which particular CPU or platform was it running. Right? So once it knows the context, then it can clearly articulate and summarize what's going on. As you can see, it's telling us it's limited by the backend pressure. There's also some front end pressure, but that's not the major bottleneck. There's also some lost cycles around 16%, which it clearly points out. And it also is trying to connect that back to IPC, which is the useful work. That's very nice of LLM. Once it tries to summarize, it now gives like rank bottlenecks. So definitely your backend is your dominant top level limiter. We should be looking at the backend stalls. There's also core pressure, so LOB, which you mentioned. So it's just nothing but load store. There's also IXUs, which is the integer execution pressure. So there's definitely load store pressure, integer pressure. There is no ROB full pressure, which is commit side backlog pressure. So that's nice. There is memory side backend stalls led by L2 misses. So we should be looking at data cache L2. And there's also speculation waste, which is why lost is around 16%. That's a major share. For example, there are two classifications: the branch mispredicts and also the other clears. So there's definitely speculation wastage that we should be avoiding, and the workload appears overwhelmingly integer rather than floating point heavy. Now, coming to the recommendations, this is coming from some of the architecture, and also ARM specific documents that it was trained on. So it's telling us now prioritize investigating your data working set, especially around L1. You see there is L2 misses, so definitely we want to look at the working set, make sure it fits our L2 cache to reduce the L2 misses. These recommendations are tied back to the source. So if you see it's giving these recommendations, it's also telling us it's ARM specific and some of it is workload specific, right? For example, it's telling go look at the hottest Go functions, right? So that is very specific to the workload. This was a Go workload. So it's trying to see if there is pointer heavy traversals. Maybe we can go look at that. Also, look at branchy control flow, because there is a lot of lost that we have seen that was reported. Now we know there is some amount of bottlenecks around L2 cache mess. So definitely I would look at perf record, because that's essentially your next step, trying to look at the actual functions back to your source code where there are lots of L2 cache misses, right? So once we get to the actual source code line, and then you can work through your data structures, trying to minimize your working set so that it can fit the L2 cache. So that would be your practical next steps to fix this particular issue.
This was wonderful. This was a great tour of a really useful tool. One of the things that people don't really realize is how much of an impact you can have on performance by coding in a way that doesn't go with the grain of the CPU. And by understanding a little bit more how the CPU pipeline works and instrumenting that CPU pipeline so that you can see where you're costing time, it really does give the developer a lot of power to squeeze every last ounce of performance, particularly in critical path performant code. So thank you very much for this guide. This was wonderful. And thank you for joining me today. And I look forward to seeing you and everyone else at a future edition of the Ampere Developer Impact. Thank you all.